dimension of time corresponds here to both A and B having a change in their passage of time. If we examine the mathematics for measuring decay rate, the decay rate can be associated with the periods of time component, and the mean lifetime can be associated with the passage of time component. Since the base expression for mass equals the absolute value of t prime times t squared, there are two possible observations. First, we are dealing with decay rates of time, so we can set the passage of time as the vertical component for both b minus b asterisk and a asterisk minus a. This forces the period of time coordinate to be different between b minus b asterisk and a asterisk minus a, resulting in a time reversal asymmetry. The longer the lifetime of a particle, the less uncertainty there is in the mass energy. The shorter the lifetime of a particle, the more uncertainty there is in the mass energy. On the other hand, we are using a model compatible with massless particles, so we can set the present time as the vertical component for both b minus b asterisk and a asterisk minus a instead. In this case, the period of time coordinate is different between b minus b asterisk and a asterisk minus a, resulting in a different type of time reversal asymmetry. In the first case, there is a mass invariance, whereas in the second case, there isn't. In the second case, b minus b asterisk and a asterisk minus a can both have the same passage of time, that is, the same mass, though there is a break in simultaneity. Re-examining CPT symmetry, time reversal asymmetry is equivalent to a charge parity asymmetry. If we take both types of time reversal asymmetry, where the passage of time coordinate values are inversely proportional to their corresponding linear time values, then the uncertainties between b minus b asterisk and a asterisk minus a smooth out, and a relative to b equals b relative to a, even though a relative to a does not equal b relative to b. This isn't a contradiction. This is an identity crisis, where the Pauli exclusion principle and the inclusion principle correspond with quantum entanglement. If a equals b, then a over b equals 1, and the identity constant is 1, meaning there is only one particle, physical state, field, etc., depending on the application. If a is greater than b, then a over b is greater than 1, and there are at least two particles, states, fields, etc. When a over b is 1, this corresponds with the inclusion principle. When a over b is greater than 1, this corresponds with the exclusion principle. In quantum mechanics, it is impossible to know both the particle's momentum and position simultaneously within an accuracy greater than h bar. This is known as Heisenberg's uncertainty principle. Using three-dimensional time, we can apply both the inclusion principle and the exclusion principle simultaneously and account for the uncertainty principle, allowing for the basic existence equation to apply generally to quantum mechanics. We can argue that charge parity asymmetry and time reversal asymmetry are indicators that CPT symmetry is incomplete as a fundamental symmetry of physical law. The basic existence equations can account for mass invariance using three dimensions of time. So how do we account for an invariance or break in this symmetry? M violation. What is M violation? Since charge parity and time reverse symmetry are equivalent, charge parity and time reverse symmetry together in this three-dimensional time model is equivalent to mass symmetry. M violation becomes central to the quantization of gravity. Using the classical gravitation equation, Kepler's second law, and substituting a temporal radius for r, we get the following. If we assume Einstein's equivalence principle, a variance in acceleration or mass would indicate an inequality, and t squared could not equal 1. However, If the two masses are significant,
水飲みました。水。スポーツドリンク飲みました。はあ。
masses are experiencing the same acceleration,
泉号。
though not in the same way. Looking at the passage of time component in the temporal evolution of mass, the relationship between temperature, mass, and so on are byproducts of viewing the universe through an inertial frame of reference. Referring back to the sine 2b measurement, this double angle gives us a value of approximately 0.69. This is almost the value for the sine of 45 degrees, suggesting that the time-dependent parameter of CP violation in B meson, as predicted by the CKM model, may correspond with a phase transition. In our model, this phase transition could be between cross-conjugate pairs or between forward time particles and reverse time antiparticles. The transformations between left-handed to right-handed or right-handed to left-handed fermions, which is associated with generating a mass associated with weak interactions and the neutrino seesaw mechanism, is better understood through cross-conjugation and cross-symmetry. We can speculate that the values associated with dark energy correspond with phase transitions of quantum fluctuations over periods of time that correspond with the history of the universe. This suggests that there may be a relationship between the time-dependent parameter of CP violation in B meson decays, predicted by the CKM matrix, and the values associated with the lambda CDM model of the universe. These may correspond with the same phase transition, but reflected on severely distinct timescales. According to quantum vacuum zero-point energy, the lowest possible energy a quantum mechanical system can have is the ground state, which too undergoes quantum fluctuations. Symmetries between beta decay-like and reversed anti-beta decay-like phenomena could oscillate in a time loop as a temporal superposition of a hydrogen atom-like structure. These diagonal symmetries appeared to take into account charge parity violation. A forward and reverse time loop model resembles aspects of Heisenberg's uncertainty principle, incorporating a new principle into quantum entanglement, the inclusion principle. The inclusion principle and the Pauli exclusion principle work together to account for quantum entanglement, but in a new way. The basic existence equations and three-dimensional time can be applied to quantum entanglement, creating a dichotomy between the Pauli exclusion principle and a new concept, the inclusion principle.
it's a little technical, but very paradoxical, is that we've had a rule back for atoms that no two electrons can occupy the same state. It's called the exclusion principle. And we thought we understood that that was necessary according to quantum mechanics and relativity. It has to be. And with the quarks, we find the exact opposite. Two particles tend the exact opposite. Seems to be contradictory in principle. We don't find experimentally any such particles. Now everybody's looking for them. But it looks as if they exist at all, they have to be extremely heavy. Then the problem is, very good, if they're extremely heavy, how, compared to a proton, say, how is it when you put three of them together, you get a light object that's not heavy, like the proton? There are technical ways of arranging it, but they're always complicated. The situation is, as it always is when we're near the answer, it looks much simpler than it has any right to be. And the question is, what way do we have to think about it so that we understand its simplicity? That's where we stand now.
Starting from a quark soup of quantum fluctuations, there is some probability for structures to form with varying degrees of stability. For instance, some quark configurations, such as mesons, are not very stable, whereas other configurations, like neutrons or protons, are more stable. Using cross-symmetry and cross-conjugation, we can create a neutron from quark fluctuations. From this, we can transform a neutron into a more stable proton. Because protons carry charge, a virtual electron-positron pair has a...
500円です。